Hello guys, welcome back. So here we have another question from GATE 2022 on communication systems. Consider communication over a memoryless binary symmetric channel using a 7-4 Hamming code. Each transmitted bit is received correctly with probability 1 minus epsilon and flipped with probability epsilon. For each code word transmission, the receiver performs minimum Hamming distance decoding and correctly decodes the message bits if and only if the channel introduces at most one bit error. For epsilon equal to 0.1, the probability that a transmitted code word is decoded correctly is dash. So to answer this question, we need to first know what is a memoryless binary symmetric channel and what is a Hamming code and what is this 7,4. Okay. So first let us look over the memoryless binary symmetric channel. Memoryless binary symmetric channel. So memoryless means for each data, right, it only depends on that particular data. It does not depend on either the previous data or the next data. So if it only depends on that particular data, then we come to the symbols. The symbol is given as binary. Binary means 0 or 1. So we have two symbols, 0 and 1, and it is a symmetric channel. So which means that, let's say 0, when it transmitted, it has a probability of 1 minus epsilon to remain as 0, and there is a probability of error of epsilon where it is flipped to 1. So it is symmetric, meaning even if it is 1, it has a probability of error of epsilon of flipping to 0 and 1 minus epsilon of remaining 1. So here the probability distribution is symmetric for your 0 and 1. So that is what is your memoryless binary symmetric channel. Okay. So now next we come to a Hamming code. So this is your channel. So Hamming code is your error correction coding. And in this particular case, it is given 7-4 Hamming code. So what this means? So let's say you have a 4-bit input. Okay. So let's take 0, 1, 0, 1. Okay. So now I know here there is a probability that your any one of the bits will get flipped, right? For each of these bits, there is a probability of epsilon that it will get flipped, right? So if I just send this 4 bits, then the probability of error will be depending on that epsilon. Now what I'll do, let's say for each of these I send twice. So now whatever error I'm making, or let's say I send it thrice, okay? And in the receiver side, I take the maximum of 3. So maximum of 3. So in 3 of them, if all 3 are 0, I'll take it as 0. If 2 are 0 and 1 is 1, I'll take it as 0. If 2 is 1 and 1 is 0, I'll take it as 1. So whichever occurs maximum number of times, I'll take that one. So in this way, I'm reducing the error, right? So here, each of them, the probability of error is epsilon. But here, what is the probability that any two of them will be flipped? So it will be like order of epsilon square, right? So I'm reducing my error in this way. Similarly, Hamming code is one such error correction coding. So in this, what happens is, so we'll leave out the places where this 2 power n comes. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, right? So we leave out these places. So 1, 2, 3, 4, 5, 6, or it is like this, right? 3, 4, 5, 6, 7, 8. So here it is 7, 4 means only we have 7 code. We are taking 4-bit input. We are adding 3 redundant bits to make it a total of 7 bits. Okay. And we'll leave out 1, 2, and 4 here. So then the remaining things we'll fill with the data. So whatever the data is, which we took as 0, 1, 0, 1, right? So we'll fill that here, 0, 1, 0, 1. Now what do we fill here, these redundant bits? So we can either fill it using even parity or odd parity. So for the filling ones place, right, we take all the bits in the position of wherever x1 comes. Okay, so what and all comes, it is like 1, 3, 5, all the odd numbers, right? All the odd numbers is included. So 1 is nothing but 0, 0, 1, 3 is 0 1 1, 5 is 1 0 1, 7 is 1 1 1, and so on. So all these combinations we take. So here what and all are there? So here in ones place we need to fill anyway. So leave it. So 3, 5 and 7 are there. So what are those? So we have 1, 0 and 0. So to make it even parity, the number of ones should be even, let's say. So what should be your ones place? Your ones place should be 1, since here odd number of ones are there. So I'll put 1 here. So now you come to 2. So here similarly, whatever ends with 1 0, 2, right? So what all ends with 2? 1 0, 2, 6. So this is 1 0, this is 1 1 0, and we can also have next is 1 0 1 0. And by the way, this can also be x. So the next number is actually 3, 1 1, right? So then we have 6, 1 1 0. Then we can also have 1 1 1, which is 7. So in whichever position the 2 is becoming 1, all those we need to take, and then we need to do the even parity and put it at 2. Okay. So here what all we have? We have 3, 6 and 7 only. So at 3 we have 1, at 6 we have 1, at 7 we have 0. So it is already having even number. So your 2 should take value of 0. So here we need to put 0. So you can also observe that when we are filling these, the other 2's and 1's never come into picture. When we filled 2, 1 and 4 never came into picture. When we are filling 1, 2 and 4 never came into picture. Because we are taking in this format, right? For 2, what is the necessity? For 2, this should be, for 1, what is the necessity? This should be 0, right? This should be 0 and 1. So that is completely excluded in 2. For 4, what is the necessity? This should be 1. This 2 should be 0, right? So once you have 1 here, then your 2 never comes, right? So they are always exclusive of each other. So next we need to find for 4. So for 4 what it is, you need to have something like this. So what and all is possible? 4 is possible. This is 1 0 0. Next is 1 0 1, which is 5. 1 1 0 6. 1 1 1 7. So it includes 4 5 6 and 7. So which is 5 6 and 7 is 0 1 0. So what should be your 4? It should have even parity, meaning 4 should be 1. So then you fill 1 here. So now this is your newly generated bit. So this is 0 1 0 1 1 0 1. So 0 1 0 1 1 0 1. So you initially add 0 1 0 1 0 1 0 1. Then you convert it to this. So what are the redundant bits here? This one, or I'll underline. So this one, 3 4, right? 1 2 3 4. So these are your data and these are your redundant bits. So now on the receiver side, how will you find which one has made the error? So let's say in some position there is an error. So like, can we take this position? This is nothing but fifth bit, right? So 1 2 3 4 5. So let's say the fifth bit flipped. So it become 1 1 1 0 1. So this bit has flipped, right? So then we need to be able to find it. So how will we do that? Again, here also we consider the even parity. So for 1 2 4. So for 1 we take the even parity of 1 3. So if you go back, 1 3 5 and 7. So here what do you get? So 1 is 1, 3 is 1, 5 is 1, 7 is 0. So here you get an odd parity. So to make it even, what you have to add? You have to add one more, right? So let's keep this aside. So for 2, what all we had? 2 we had, then 3 we had, then 6 we had, then also 7 we had. So 2 3 6 7. 2 is 0, 3 is 1, 6 is 1, 7 is 0. So here we have even parity, we need to add 0. So next is 4. So 4 we add 4, 5, 6 and 7. So 4 is 1, 5 is 1, 6 is 1, 7 is 0. So here you have odd number, so you need to put 1. So now if you take these bits and arrange it as 1 0 1. So this 1 comes here, 0 comes here, 1 comes here. So this is corresponding to 5. So it denotes your, shows your which bit has made an error, or which position made an flip, made an error or flip. So this will only be possible, this error detection is only possible when only one of the bit is flipped. If more than one is flipped, then this error correction will not be possible. So now you know which position is flipped. So now you can correct it. So you can correct it back to 0 1 0 1 1 0 1. Then you can discard these bits 1 2 3. You can discard and you can only take 0 1 0 1. So this is your transmitter thing. So that is what they have also mentioned in the question. For each code word transmission, the receiver performs minimum Hamming distance decoding. So that is the decoding we saw now, and correctly decodes the message bit if and only if the channel introduces at most one bit error. Okay, so now that is clear. Now we need to find the probability that a transmitted code word is decoded correctly is dash. So probability to decode correctly. So what is it being? So it has two things, right? There is no flip happened, plus probability of no flip happen, plus probability of single flip happen, one flip happen. Because only if at most one is flipped, we can correct it and get the actual code without any error. So these two probabilities we need to find. So what is the probability that no flip happened? So what is the probability of flip? Probability of flip is epsilon, right? And for how many code word we are talking about? Here we are talking about 7, right? So for each of 7 bit width, the input is 4 bit width, we are getting a 7 bit width, and it is correcting only within that, right? It is not going to the other code words. So we need to see for a code word of 7. So for 7 code word it is. So what is the probability of no flip happen? So it is 1 minus epsilon 7 times. So power 7 plus what is the probability of the one flip happen? So it can happen in any one of the 7 places. So 7c1 into probability of one flip happening is epsilon into rest of the 6 are unflipped. So this will be your total probability. So 1 minus epsilon is 0.9 power 7 plus 7 into 0.1 into 0.9 power 6. So this we can calculate. So they have asked us to round off to 2 decimal places. So here you can take up to 3 decimal places. So it is 0.478 plus 0.372. So adding this, it comes up to 0.850. So this is your probability to decode the message correctly. So this is your answer. So actually all these theory you should have known beforehand. Your solving part is just this last thing. From here only it is solving. Right? It is very simple and easy.